So next, let's talk about breadth first search, or BFS for short. And just like DFS, this actually doesn't necessarily need to be applied to a binary search tree. It could be applied to any tree, whether it has that sorted property or not. But the idea here is that we want to traverse this tree layer by layer. So breadth first, meaning we want all the closest nodes first, and then we want the next layer of the closest nodes and then continue doing that. We don't want to go depth first, right? We don't want to, go all the way to the bottom before we traverse the closest ones. We want to do it the opposite way. We want to do this layer. And typically what we do with breadth first search is we go left to right, but you don't necessarily have to do that. But for trees, it usually makes sense to go left to right. So traversing this, and let's say we're printing each value, we would have the first node, the root node, we would print 4, and then we would go to the next layer. How would we do it? Well, if we're going left to right, we should go to the left child first. So from here, we print 3, and then we do the right child. So from here, we print 6. Now, if we print 6 after we print 3, how are we going to get to this node? Because now for our breadth first search, we want to do this next level. We want to do 2, then 5, then 7. So how are we even going to get to the 2? I mean, assuming we had a pointer here when we were at 3, next we're going to have a pointer here when we're at 6, we kind of have to save that pointer. So this algorithm actually doesn't really suit recursion very well, because it's not like we're going to recursively traverse this and then recursively traverse this to get that breadth first search. So we're going to have to do this iteratively, but let's continue. Next, we would want to traverse 2. How do we know we want to traverse 2? Well, we're going to traverse all the children of this node. Just like before, first we processed 4, and then we processed all of its children. Next, we processed 3 and 6, and now we want to process all the children of these nodes from left to right. So we get all the children of 3 and then print them. So we get 2, then we get all the children of 6, and then we print them. So we get 5, and then we get 7. Now this didn't, create anything super useful for us. We didn't print it in order or anything, but BFS is definitely a useful algorithm to know. It could also be called level order traversal, because we're going level by level in this tree. So the code for it is going to be pretty interesting. Remember how I said that as we process a node, after that, we want to process the children of that node from left to right. And then as we process, another level or another node here, we want to process its children from left to right, and then process its children from left to right. So as we go through every node and process it, we should take the children of that node and add it to some data structure to remind us to next process these nodes, and then next process these nodes, and then next process these nodes. Well, there aren't any more nodes here for us to process, so that's how we know we can stop. What kind of data structure can we use? Well, actually, we've already implemented the data structure that we need, and it's called a queue, because we're going to add these elements first in, first out. So if after processing this, we add its children in the order left to right, we add the 3 and then the 6, those are added to our queue, we're going to process these first in, first out. We're going to process the 3, and then we're going to add its children to the queue. So at this point, we would have a 6 and a 3 in our queue. We're gonna do it first in, first out. Since the 6 was added first, we want to process it first, and that makes sense because we want to finish this entire level before we get to the next level. Let's take a look at what the code for this would look like. So this is the Python code, but it would be very similar in other languages. The idea is that we're gonna use a queue. In this case in Python, it's called a deck, which is a double-ended queue. But it's basically the same queue that we implemented earlier in the course. So we have a queue. For our BFS, we're given the root of some tree. Now, of course, it could be empty, in which case we're not going to add anything to our queue. But in this case, suppose we were given this node. That would mean we added this node, not the value, but the node itself to the queue. So as of now, our queue has a single element, this node. In this case, suppose we actually wanted to count the levels as well. Like as we print these values, we say this is level 0, this is level 1, this is level 2, etc. We don't have to do it that way. It would be simpler if we didn't need to do it that way, but let's do it like this because sometimes this can be more useful and this requires a couple extra lines of code. So it's a little bit more complex, which is why I'm showing it. But here, we're at level 0. Is the length of our queue greater than 0? Well, this is our queue right now, so it is greater than 0. We can print the level now, so level 0, and then we're going to print every node in the 0th level. There's only going to be one node in the 0th level because there's only one root node for every tree. So from our queue, we're going to pop. In Python, it's called pop left. But you can just kind of imagine this is what the queue looks like. We add elements like this. So we're adding to the right and we're popping from the left. This is just our standard queue pop. We're popping from the opposite side that we're pushing. So it's first in, first out. So we pop the node 4, we get it, we print the value of it, then we check its left and right children. We want to take its children and add them to the queue. But if its left child is null, we don't want to add it to the queue. So we check, is the left child non-null? Yes, it is. So we add it to the queue. It's important to add the left child before the right child if you want to traverse them, like if you want to traverse each level like this. Of course, we could do it the opposite way if we really wanted to, but usually it's more common to do left from right. So we add the left to the queue, then we add the right child to the queue because it's also non-null. So this is what our queue looks like so far. We've printed 4 so far. And at this point, actually, our inner loop is done executing because we took the length of the queue, which initially was 1. We just had a single value in it, and then we're finished. Now, we did add a couple more elements to the queue, but in this case, what this does is it takes a snapshot. So we just took an integer 1, and we had a loop that iterated 1 time because we only had 1 node. It's basically like we have a constant value here. Right? We only calculated the length of the queue a single time. So we did that, and now we finished this inner for loop. So we increment the level by 1, and then we go back to our outer while loop and check, is the length of the queue greater than 0? We have 2 elements in the queue, so it is greater than 0. So we print the next level, level 1, if we're starting at 0, and then we pop from the left of the queue. So we would pop the leftmost. Let's say this is the leftmost because we inserted it first. So we pop it, we print it, we check its children. It has a left child, so we add it to the queue. It does not have a right child, so we don't add it to the queue. So we've printed 4 and 3 so far. So our queue is going to look something like this. We first had the 4 on the queue, we popped it. Then we had the 3 and the 6 on the queue. We just popped the 3 and printed it. And we still have the 6 on the queue, and we just added the 2 to the queue. But we're going first in, first out. So next we're going to pop the 6. We pop this one. We print its value, we look at its left and right children. First, the left child, it's non-null, so we add it to the queue. By the way, I'm drawing it as the value, but in reality, in the queue, we would actually have the node itself because when we pop the node, we want the pointer to the left and right child of that node. We wouldn't have that if we were only storing the value. It's important to store the actual node itself. So we do the same thing with the right child. It's non-null, so we add it to the queue. And at this point, we continue. So we pop the next node in the queue, which is 2. We can print 2. And 2 does not have any children, so we don't add anything to the queue. So you can kind of start to see how this is going to finish up. Now we pop the 5. We can print the 5. It's getting a little bit messy over here, but it's not so important, the values that we're printing themselves. It didn't have any children either. We pop the 7 next. It doesn't have any children. We will print the value or do something with it. And then this is our level order traversal. At this point, our queue is empty. So we stop, and that's gonna, in terms of code, gonna stop here. The length of our queue is not greater than 0, so we stop. By the time though we got to the last level, when we were here with a 2, 5, and 7, we would have taken the length of the queue to be 3. We would have executed this loop 3 times, popping a node each time, and we would have tried to add the children, but the children don't exist, so our queue at that point would have been empty. We would have gone back up to the outer while loop. The length of our queue is now empty, so we stop. So that's the idea behind breadth first search. Now, what's the time complexity? Well, people get really confused when they see nested loops. People automatically assume when you have nested loops that the time complexity is going to be n squared, but that's not the case here. And the simplest way to understand that is just by looking at what we did. You watched me go through this tree. We only traversed each node once, right? We printed each node once. We added it to the queue once, and then we popped it from the queue. So you could say for each node, we had, let's say, 2 operations. Technically, you could say we have 3 because we're printing the node, we're appending the node to the queue, and then we're popping it, but it doesn't matter. It's some constant c times n, where n is the number of nodes. So this is the number of operations we did. We know that reduces to big O of n. Don't worry so much about, the nested loops. Yes, we have nested loops, but clearly the total number of operations we're going to do is big O of n. So that's the time complexity. Just like any traversal, we visit every single node once, so just like DFS, the time complexity is going to be the size of the data structure that we're traversing, which is the number of nodes. I mentioned DFS is probably the most common algorithm you'll use. BFS is probably the second most, and maybe it is the most common. And we definitely have not seen the last of BFS. I'll tell you that much right now.